Look up at the night sky. What do you see?
A vast expanse of darkness sprinkled with countless twinkling points of light. Each of those points is a star, a giant ball of burning gas that emits light and heat.
Some stars appear brighter than others because they are closer to us or because they burn with greater intensity. Others are so faint that we can only see them with powerful telescopes.
Stars are the building blocks of galaxies, and galaxies are the building blocks of the universe. Our own galaxy, the Milky Way, is home to hundreds of billions of stars, and there are billions upon billions of galaxies in the observable universe.
Each star has a life cycle, just like living organisms on Earth. They are born, they live, and they die.
But unlike the fleeting lifespans we experience, the lives of stars unfold over millions, billions, or even trillions of years. The life cycle of a star is a story of gravity, nuclear fusion, and the relentless passage of time.
It's a story that begins in the cold, dark clouds of gas and dust scattered throughout galaxies. It's a story that ends in spectacular explosions, leaving behind remnants that continue to shape the cosmos for eons to come.
This is the story of the Symphony of the Stars, a cosmic ballet of creation and destruction that has played out since the dawn of time. This is a story that connects us all, for the very atoms that make up our bodies were forged in the fiery hearts of stars long ago. We are, in a very real sense, children of the stars. Stars are born in vast, cold clouds of gas and dust called nebulae. These nebulae are like cosmic nurseries, providing the raw materials and conditions necessary for star formation.
Imagine a cloud of interstellar gas and dust, much larger than our solar system, drifting through the galaxy. This cloud is not uniform. It has regions of higher and lower density.
Within these dense regions, gravity begins to pull the gas and dust together. As more material clumps together, the gravitational pull increases, drawing in even more matter. The cloud begins to collapse under its own weight, like a collapsing skyscraper.
As the cloud collapses, it begins to spin faster and faster, just like a figure skater pulling in their arms. This spinning motion flattens the cloud into a rotating disk.
At the center of this swirling disk, the material becomes incredibly dense and hot. Temperatures and pressures soar as the collapsing cloud converts gravitational potential energy into heat. This central region is called a protostar, the precursor to a star. If the protostar gathers enough mass, the temperature and pressure at its core will eventually reach a critical threshold. This threshold ignites nuclear fusion, the process that powers stars.
In nuclear fusion, hydrogen atoms are forced together under immense pressure, fusing to form helium and releasing a tremendous amount of energy. This energy radiates outward from the core, creating an outward pressure that balances the inward pull of gravity.
The protostar has now become a star. Once a star achieves nuclear fusion in its core, it enters a long, stable period known as the main sequence. This is the longest stage in a star's life, and it's where our own sun currently resides.
During this phase, the star exists in a state of equilibrium, with the outward pressure from nuclear fusion balancing the inward pull of gravity. This balance can be maintained for millions, billions, or even trillions of years, depending on the star's mass.
Massive stars burn through their fuel much faster than smaller stars. This is because the intense gravity of massive stars creates extremely high temperatures and pressures in their cores, accelerating the rate of nuclear fusion.
Think of it like a car engine. A larger, more powerful engine will burn through fuel much faster than a smaller, more efficient engine.
Eventually, every star exhausts the hydrogen fuel in its core. When this happens, nuclear fusion in the core ceases, and the outward pressure that once balanced gravity disappears.
The core begins to contract under its own weight, becoming denser and hotter. As the core contracts, it heats up the surrounding layers of hydrogen, igniting fusion in these outer layers.
This fusion in the outer layers causes the star to expand dramatically, transforming it into a red giant. Red giants are much larger and cooler than their main sequence counterparts, hence their reddish appearance.
If you could replace our Sun with a red giant, its outer layers would extend beyond the orbit of Mars, engulfing the inner planets, including Earth.
And so, the star approaches its final stages, leaving behind a legacy that continues to shape the universe.
Section 5. Supernovae, the spectacular deaths of stars.
The fate of a star after the red giant phase depends on its mass.
Smaller stars, like our Sun, will eventually shed their outer layers into space, forming a beautiful expanding shell of gas called a planetary nebula.
The core of the star will remain behind as a small, dense object called a white dwarf.
Massive stars, however, are destined for a much more dramatic end.
These stars continue to fuse heavier and heavier elements in their cores, creating elements like carbon, oxygen, and even iron.
However, fusing iron requires more energy than it releases. So when the core of a massive star is filled with iron, fusion stops.
Without the outward pressure from fusion, the core collapses in on itself in a fraction of a second.
This collapse triggers a shock wave that tears through the star, blasting its outer layers into space in a cataclysmic explosion called a supernova.
Supernovae are among the most energetic events in the universe, briefly outshining entire galaxies. Section 6. Stellar remnants, white dwarfs, and neutron stars.
After a supernova, the core of the star is compressed to incredible densities, forming a stellar remnant. The type of remnant depends on the mass of the core. If the core is less than about 1.4 times the mass of our Sun, it will form a white dwarf. White dwarfs are incredibly dense objects, about the size of Earth, but with a mass comparable to the Sun. Imagine squeezing all the mass of the Sun into a sphere the size of our planet.
If the core is more massive, between 1.4 and 3 times the mass of the Sun, it will form a neutron star. Neutron stars are even denser than white dwarfs, squeezing the mass of the Sun into a sphere only a few miles across. A teaspoon of neutron star material would weigh billions of tons on Earth. Section 7. Black holes, gravity's ultimate triumph.
If the core of a collapsing star is more than 3 times the mass of the Sun, gravity overpowers all other forces. The core collapses indefinitely, forming a region of space-time where gravity is so strong that nothing, not even light, can escape. This region is called a black hole. Imagine a giant cosmic drain, pulling everything around it inward. That's what a black hole is like, except that it's not a hole in space, but rather a region of extremely warped space-time.
Black holes are invisible because they don't emit light, but we can detect them by their gravitational effects on surrounding matter. Section 8. The cosmic recycling plant.
Supernovae are not just destructive events, they are also crucial for the evolution of the universe. The intense heat and pressure of a supernova explosion create heavy elements that were not present in the early universe. These elements are scattered into space, enriching the interstellar medium with the building blocks of planets, life, and even you and me.
The iron in your blood, the calcium in your bones, the oxygen you breathe, all of these elements were forged in the fiery hearts of stars and scattered across the cosmos in supernova explosions. Without supernova, the universe would be a very different place, devoid of the complex chemistry needed for life as we know it.
In this way, stars and their life cycles are part of a grand cosmic recycling plant. Stars are born from the ashes of dead stars, enriching the universe with heavy elements that will eventually form new stars, planets, and perhaps even life. It's a beautiful and awe-inspiring cycle that connects us all to the vastness of the cosmos.
Section 9. Our place in the starlit cosmos.
The next time you look up at the night sky, remember that you are witnessing a snapshot of a cosmic ballet that has been playing out for billions of years. Each star you see has a story to tell, a story of birth, life, death, and rebirth.
We are all connected to this cosmic dance, for we are made of star stuff, forged in the fiery hearts of stars long ago. The very atoms that make up our bodies were once part of a star, and will one day be part of a star again. It's a humbling and awe-inspiring thought that underscores our place in the grand tapestry of the cosmos.
So take a moment to appreciate the wonders of the universe around us. Explore the night sky, learn about the stars, and share your passion with others. For in understanding the universe, we come to understand ourselves a little better.